Hey guys, welcome back to my channel. So here we'll be working through the next 4 questions, yeah? And in this part, we're going to do number 8, 9, 10, and 11. Okay, so let's just jump straight in then, yeah? So for question 8, we're given some kind of figure, and this is actually a cubic graph. We know it's cubic because it hits the x-axis at 3 points. So one here, one at the origin, and another at this point here. Now, figure 2 shows a sketch of part of the curve of equation y equals x times x plus 2 and x minus 4. And these are the roots of the equation. And the way this works is that if you just set y to 0, you're going to have x equals 0, which is the origin. You got x plus 2, which means that x has to be minus 2. So this is the root here. And because you got x minus 4, the other root will be x equals plus 4. So you got here 4, 0, and minus 2. Now, let's just move on to the next part. Now, looking at the question, it says that the region R1 shown in figure 2 is bounded by the curve and the negative x-axis. Show that the exact area of R1 is 20 over 3. Okay, so let's just focus on A and ignore parts B and C for a second. Okay, so let's just pull out R1 for a second, yeah? Now, just going back from what we said that the roots of this equation have minus 2 on the left side and 0 on the right. And now to work out the actual area of the shape, we can't use the traditional method. We have to use integration, yeah? And the general form is like that. It says that the area is equal to some integral with some limits, and the limits are basically your x-axis, yeah? It's from where to where. So in this case, L is your lower bound, so we can say it's from minus 2 up to its upper bound, which is 0. And then we need to integrate some equation of y. And our equation of y is here, okay? It's x times x plus 2, x minus 4. Now, to deal with this one, what I would recommend, guys, is I'll just expand this fully, yeah? To get a nice cubic expression. So let's deal with the second 2 brackets here. To expand a quadratic, we just do term by term. You should get something like that. X times x squared, x times minus 4 is minus 4x, plus 2x minus 8. And then collect the like to the 2 terms in the middle, because you've got minus 4x and plus 2x. That gives us a negative 2x. And the last step, just times everything by x. And everything should increase by 1 power. So you should get x cubed, minus 2x squared, and then minus 8x. Alright, great. Now that you've got this equation, we can just substitute this back into the area equation. So replace y with that. And again, replace your limits. So you've got u, which is the upper limit, which is 0, and the lower limit is negative 2. Now, that's our value for R1. So integrating this step by step. And remember, to integrate, you just increase the power by 1 and divide it by itself. So it will look a bit like that. You can get x to the 4th over 4, x to the 3 over 3, and then x to the 2 over 2. And then because you've got limits, we put a nice square bracket with 0 and minus 2. So what this means now, we're just going to have to substitute all these values with 0 first, and that's kind of easy. If you replace everything with 0, you're just going to get 0. Now, if you replace everything with negative 2, so copy out of negative 2, you get something like that. And thankfully, this is a calculator exam, guys, so you can just whip this all in the calculator, and you'll definitely get, well, inshallah, you get 20 over 3. And that's it. So that's part A done. So let's just keep this and move on to the next bit. Now, on the second part, it says that the region R2, also shown shaded in figure 2, which is, again over here, is bounded by the curve, the positive x-axis, and the line with equation x equals b. Now, be careful, guys, yeah? They said x equals b, but this does not mean like we have to, it's where the curve intersects x-axis. Now, this is just a random point b, yeah? Now, it says that b is a positive constant and is somewhere between 0 and 4. We know this root here is 4, so this is going to be less than 4, but bigger than 0. Now, given that the area of R1, which is the first bit, is equal to area of R2, meaning this part is 20 over 3, verify that B satisfies this equation. Alright, this is kind of different to your typical show me, guys, because show me means you have to get to that step. This is kind of tricky because this is, in fact, if you expanded it out, is a quartic equation. Quartic means you literally go to the power 4. So that's kind of a bit something. But let's just think about how to get there. Now, they told us that the area of R2 is equal to area of R1. How about we just use, find the area of this using integration from 0 to b instead. So doing the same thing, using the same expression, we can say integrating from 0 to b of that equation, which we've seen, the cubic one, it should give you 20 over 3. Well, if we had to use the same method, if we integrate it step by step, you get x to the 4th and so on. Basically, you can copy the last one. The only difference now is that you replace all the x's with b and x with 0. Well, we saw last night that when you replace a 0, you get nothing. If you replace a b, you get that. So that's okay. And again, this is all equal to 20 over 3. Yeah, so guys, at this stage, we just want to go ahead and just clear that fraction, yeah? So I'm going to go ahead and just multiply these lot by 4, okay? Because what happens when I do that? If you multiply by 4, well, that cancels out. In your calculator, you can write 2/3 times 4, gives you 8/3. 8 over 2 times 4 is just 16, conveniently. 20/3 times 4 is, well, 8 over 3. And once again, let's multiply this by 3 to clear out the 3's, yeah? So you're going to have the same expressions of 8b cubed and 80, so that stays the same. And you're going to get 3b to the power 4 because you multiply that by 3. Times 16 by 3, you get 48. And that's it, guys. You literally have this. So once again, let's just pull this to a fresh page, yeah? If you remember, we want it to equal 0. So let's just minus 80 now. Now, just thinking about what to do next. We want to somehow factorize this, yeah? But there's a cool method because actually it says verify. It doesn't say show that, meaning you can kind of work backwards. So instead of factorizing this, we can go ahead and expand this previous expression, right? So we can say that, okay, let's verify this by working backwards and expanding above. Because I'm not going to lie, guys, sometimes it's a bit tricky to kind of go from here to there. You can technically, I mean, you could, do long division twice. You'll get that. That's actually a legit method. You can do long division. But let's do it this kind of way, yeah? So let's go ahead and expand this bracket. So let's just pull it out for a second. Now, we know we've got b plus 2 squared, meaning we've got 2 brackets, yeah? So what we could do, I'm going to go ahead and expand these first 2 brackets first, because they're kind of easy to do. If you do that, you get b squared plus 4b plus 4. Okay, cool. Now, I'm going to go ahead and multiply all of this by the second bracket. The nice way to do this is to distribute each of these terms to this bracket. So look like this. So all we have to do now is just multiply this entire bracket by b squared first, and then 4b, and then finally 4. Okay, so what do we get? Multiplying the first step by b squared, you should get this. Everything goes up by 2 powers of b. Multiplying the next step by 4b, you should get this. And finally, multiplying the last by 4, again, you should get this. And all this is equal to 0. Then you're left with this, yeah? So just collecting like terms, minus 20b cubed plus 12b cubed will give us just minus 8, like the one you want. Simplifying this, you should get a final result of that. And that's it, guys. There's literally nothing to it. And yeah, so we've kind of verified it. And when you verified it, just say verified, and you're done. Now, moving on to the final part. So the roots of the equation, 3b squared minus 20b plus 20, and this, by the way, guys, is actually the second bracket from here, the quadratic bit, okay, are 1.225 and 5.442 to 3 decimal places. So these are 2 roots we get from this quadratic. The value b is therefore 1.225 to 3 decimal places. So I don't know why they can repeat that, but okay. Explain with the aid of a diagram the significance of the root 5.442. Okay, so in other words, what's so special about that second root? So what it's trying to say here, why is this second root so important? I think the better question is, why are they both important? Well, when we evaluated the integral previously from 0 to b, we said that was supposed to equal 20 over 3, okay? So technically, this means that the net total area between 0 and b is 20 over 3. Now, because you got 2 values of b, you actually have 2 net values. From like 0 to 1.225, the area is 20 over 3. Also, the value from 0 to 5.442, the net total area is also 20 over 3. So it's just telling you where it is. So we can say, alright, therefore, the quartic equation tells us that the net total area between minus 2, in other words, like, because remember there's also a b plus 2 in the equation, and the other root is 0. But let's look at it visually for a second, yeah? Let's just draw a quartic graph. So let's draw a cubic equation. Now we know what the roots are. The first b root is over here, 1.225. And the second one is going to be kind of on the edge. So let's just say it's over here, just sake of convenience. Remember, this root here is 4, and this root here is minus 2. We've got a bunch of areas, yeah? R1, R2, which we know. We also got R3 and R4, which is new, just for the purpose of the example. We know that the first 2 areas is 20/3, and because we know that the net total area between 0 and b, so 0 in this point or 0 in that point is 20/3, we can actually say that these two have to be equal. Okay, they have to give you a net total return of 0. So in other words, we can say R3 equals R4. You don't need to work out, guys. So in the end, we can just say, alright, to make this sense of this equation, I think the first point is enough, by the way. But you can also say something like the areas above the x-axis, R1 and R4, must equal areas below the x-axis. So you can kind of see that if you add up these areas and subtract against these areas, you're going to get a net total area of 0, just like we assumed. And that's it, guys. I think this is just one way to explain it. I'm sure there's other ways, but all they kind of really want to say is what happens between 0 and b's. So 0 in here and 0 in that. If you get that far, then you probably got the mark. You can extend it by including the whole graph. But yeah, let me know what you guys got, yeah? We can talk about it in the comment section, because this is kind of, I'll say it's one of the trickiest questions to actually solve, because it's a bit odd, and no one's actually really seen something like this before. But yeah, let's move on then anyway. So, number 9. So given that a is bigger than b, which is also bigger than 0, and that a and b satisfies this logarithmic equation, show that you can get this equation. Okay, so I'm going to skip b for a second. Now, we just got to know some properties of logs here. First things first, when you subtract two separate logs, it's the same as dividing the terms inside. So it looks a bit like that. Log a minus log b is log a over b, and that's going to equal the right hand side. Now, a unique feature of this is that you're trying to get rid of the logs, right? If you've got two equivalent expressions, so this is saying the log of that must equal the log of this. This is implicitly telling you that the inside equal each other. So a over b equals a minus b. Now the rest is simple. To get this, to pretty much solve this, let's clear the fraction, yeah? Let's times b across. If you do that, you get this. Expand the bracket, you get ab minus b squared. Now, to get a, the subject itself, we go isolate it. So what I would do, I would probably subtract ab across, like that. Then I'll factorize it out. And then finally, I'll divide 1 minus b across, and you get something like that. Now, this kind of looks a bit like this one, except it's got a negative sign as 1 minus b. The good thing is, if you just factorize 1 minus b out, times it against the negative sign, this becomes minus 1 and plus b. Or you can rewrite it as plus b minus 1. And that's it, guys. It's shown. Now, for the second part, it says write down the full restriction on the value of b. Explain the reason for this restriction. Okay, so I'm going to pull this out for a second, yeah? Now, previously, let's just go back again. The restriction was that a is bigger than b, which is also bigger than 0. Okay, cool. Now, before we get to that restriction, let's just talk about what do we know about fractions, yeah? We know that when we're dividing things, we can't divide by 0. So essentially, b minus a can't be divided by 0. So we say that. So this essentially means if you add 1 across, b cannot be 1, because it's undefined at 1, meaning it's not possible. Now, going back to the very first restriction with a greater than b greater than 0, this tells us that, if a is greater than b and b is greater than 0, we can just focus on this a part, which is this expression. We know all of this is also greater than 0. A is greater than 0, meaning the whole fraction is also greater than 0. However, guys, it's positive. So greater than 0 means it's positive. We also know that it can't be 1, because 1's undefined, and it can't be value less than 1. Why? Because if you had like 0.5, this will give you a negative result. That ain't going to work. So we know b itself has to be bigger than 1. And that's literally it, guys. You've pretty much got the restriction. So if we combine all together, instead of saying a is bigger than b is bigger than 0, it's now going to be a is bigger than b, bigger than 1. And yeah, I think this covers this question. Now, let's go to the next one. Alright, proofs. Oof. So, 10i. Prove that for n in all natural numbers, so n literally means natural numbers. Example of natural number, guys, are like 1, 2, 3, 4, 5, 6. So just ordered numbers. There's some definition that start with 0, but that's not a big deal, yeah? Now, prove that for all n of natural numbers, n squared plus 2 is not divisible by 4. Okay, now whatever you guys do, don't just plug and play, yeah, because you can't just choose a number and hope it's divisible by 4. You kind of have to rewrite this using an actual equation, yeah? And the way we do this, we need to write an even function, an even equation, and an odd equation. So let's take one. Because we want to divide by 4, we're just going to let n equal something that's 4, like n equals 4m. And we know this is an even number because if you think about it, 4 times anything is even. I could have just said 2m, or 6m, or 8m. That's the point. As long as it stays even, it's good. Now, because we let n equals 4m, let's substitute this into the equation, yeah? So I'm going to call it a function of fm, replacing this with 4m squared plus 2. If we expand the bracket, guys, we're going to get 16m squared plus 2. Now, if we factorize 4 out of this, so let's just factorize 4 out. Let's just see what happens. You can factorize the first term, but obviously you can't factorize the second because dividing by 4, you get 2 quarters or half. And you can see that alone is not a whole number. So our conclusion for the first statement for even functions is that this function is not divisible by 4 since 2 quarters is not a whole number. And yeah, that's cool. I mean, you'd think this is it. But it says proof for all n. So this isn't all n. This is just even numbers. So we also need odd numbers. So let's let n equal an odd number. So you have an even number plus an odd number. So 4n plus 1. So whatever this is always even. Add 1 makes it odd. So this statement holds, yeah? Now repeating the process above, yeah? We're going to have 4n plus 1 squared plus 2. Expanding the squared bracket, you get 16m squared plus 4m plus 1 plus 2, which is basically plus 3, yeah? And then repeating this one, factorizing 4 out. You can do it for the first two terms. However, last time you can't, because dividing 3 by 4, you get 3/4. And then once again, the conclusion is the same. Not divisible by 4 since 3/4 is not a whole number. And then that's it. Now, to end this always nicely, you always have to say, alright, so for all n, we find that this entire function is not divisible by 4. And that's it, guys. That's a wrap, yeah? That's I done. Now, let's look at the second part, yeah? Second part is slightly, I don't know, I'll say it's easier because you can choose values. It says, given that x belongs to R, now this R stands for real numbers, yeah? Real numbers literally means anything. And by that, you can choose any value. A whole number, a decimal, a fraction. So even pi or exponential terms or logs. Anything is a real number. Anything that is not imaginary, which you can't square it by negative, is real, yeah? So anything that works in your calculator is real. Now, going back again. So given that x belongs to real numbers, the value of the modulus of this, meaning it's always positive, so whatever x value you choose, if you get a negative result, it forces it to be positive, is greater than or equal to the value x minus 9. State, given a reason, if the above statement is always true, sometimes true, or never true. Okay, this is interesting because just looking at it for a second, yeah, it's claiming that this is always greater, or this is greater than that. That's the claim. If you think about it, I mean, if you just choose any value for x, if you choose any negative value, like let's say, I don't know, like minus, let's just say 0 for a second, you get minus 28. But because you got the absolute signs, minus 28 becomes a plus 28. If you put 0 here, you get negative 9. So that's obviously greater. This is true for everything, but there's a trick here, yeah? And the trick is like, is to test some values x and make a table. I'm gonna show you my table right now. That's what I personally recommend do something like that, yeah? I write a table which has x, the first function, and the second function. I'll just plug in a value like 0, like we did. Here you get plus 28, second you get minus 9. Obviously it's bigger. Now what I would also do is I'll set both of these functions to 0 to see like when is it 0. For example, if I set the second equation to 0, you can see that x has to be 9 to make it 0. So if you plug in 9, you would realize that on the first function you get a 1, and the second one you get a 0. And for the second function, if I plug in a 0, I'm going to ignore the negative roots here. I'll plug in a 0, you get 3x minus 28 equals 0. Solve it, you get 28 over 3. Now, if you plug into the first one itself, obviously you get 0 because that's what we did. If you plug into the second case, you actually get a third. And this is the only, well, this is one of the few only times that it's actually bigger. The rest of the times the first function is always bigger. And I just test another random number like 9.5. This makes it equal. Again, this was just luck. So you don't, like, to actually show something is equal, by the way, you just make both these functions equal each other and solve for x, which will give you 9.5. And that's it, guys. And then when you do that, you make a conclusion. You say, all right, it's sometimes true since x minus 9 is greater than this when, oh crap, when x equals 28 over 3. All right, number 11. So a competitor is running a 20-kilometer race. Now she runs each of the first 4 kilometers at a steady pace of 6 minutes per kilometer. Okay, so let's just note that down, yeah? First 4 kilometers, this means 24 minutes because 4 times 6 is 24 minutes. After the first 4 kilometers, she begins to slow down. Now, in order to estimate her finishing time, the time that she would take to complete each subsequent kilometer is modeled to be 5% greater. Okay, I'm going to note that down, yeah? Than the time she took to complete the previous kilometer. Okay, so what this means now is that we're no longer doing this arithmetically. We're doing this geometrically. Okay, so it's going to be increasing by some rate. Now, for example, we know that it took 6 minutes to do a race. That means on the 5th kilometer, it will be 6 times 1.05. So it's going to increase by 5%. Likewise, the next one's going to be 5% greater than that. So the 6th kilometer will be 6 times 1.05 squared. And the next one is cubed, power 4, and so on. Okay. Now, using the model, show that her time to run the first 6 kilometers is estimated to be 36 minutes and 55 seconds. Alright, so let's just pull this out for a second. Yeah? Let's just pull it out and take our data with us. Now, we saw earlier that the first 4 is 24 minutes, the 5th is that many minutes, and the 6th is 6 times 1.05 squared minutes. Okay? the total of this, so if you just put 24 and all this in your calculator, you should get a total time of 36.915 minutes. We got the 36 minutes part right. Now for the seconds, we need to convert this decimal into seconds, yeah? Because think about it, this is 0.9 of a minute, so it's still less than a minute. Now to convert something into seconds, you take that decimal part, 0.915, times against 60, and you should get a result of 54.9 seconds, okay? So this gives you a second result. So we can just round up to 55. So we can say, therefore, the first 6 kilometers run was 36 minutes and 55 seconds. And just add the word shown to show that, you've done it. Now, let's just move on to part B, yeah? So show that her estimated time in minutes to run the half kilometer, so this is kind of like the nth term, for all values between 5 and 20. So this is from the 5th to the 20th kilometer, because the first 4 kilometers are just, the arithmetic. You just add 6. It's given by this kind of formula. Okay, so to show this is the kind of formula we need, you can kind of notice one thing. Like if you plug in, like, a little trick here, if you plug in 5 for R, you get 6 times 1.05 to the power of 5 to the 4, which is 1. So that's referencing the 5th kilometer. For the 6, if you plug in 6, you get that. So we can kind of make this easy. We just plug in, we just say the 5th is that, like we just said. The 6 is this, meaning if we had to generalize it, if we did it for the half term, it's going to be the same thing but with R. And to make it look like that, just rewrite in what they want. And again, write shown. And that's it. Estimate the total time in minutes and seconds that she will take to complete the race. Okay, so this is kind of chilled. You just need to find the total time. And we know that it took her 20 kilometers, yeah, because that's what it said in the beginning question. And we know the first 4 kilometers was 24 minutes, and then the rest is given by this kind of equation, yeah? You just got to sum them up. So we say, alright, therefore, the total time is going to be the first 24 minutes plus the next 2 terms, 5th and 6th, plus ... all the way to the last part. Now, if you think about it, if you plug in 20 for this one, we know altogether you're going to get power 16. So this means she's going to do this 16 times, yeah? It's geometrically increasing 16 times. Now, that's what we need to work out. So I'm going to just bold it there for a second and make a fresh page. And to resolve this bit, you could just use the sum of a geometric progression formula, so the SN formula. Now, the SN looks like this. For geometric series, we got Sn equals a times 1 minus r to the power n, where r is your common ratio, n is the number of terms, over 1 minus r. Now, we need to pick carefully what is our a, r, and n, okay? I think for our a, and a is always the first term, we're talking about the first term of this series. We can see that the first term is the very first thing, 6 times 1.05. Now, be careful, guys. It's tempting to write 6, but that is not your first term. Your first term is the very first thing that started the geometric, which was that. Our r is quite obvious. It's increasing by powers of 1.05. So that's it, 1.05. And n is the number of terms there are. Well, this is your first term, second term. You got 16 terms, so that's your n. Now, all you do is plug this into your formula, and you'll get something like that. 6.3 times all of that. And this is a straight up calculation. Drop this in your calculator. You get an S16 of 149 point something. Now, our total time, therefore, is going to be this quantity plus 24, which will give us 173 minutes. Point some few seconds. Now, once again, just like the previous question, we need to somehow convert this decimal bit into seconds, yeah? Now, if you recall, it's just like you take off the 0, so it'll be 0.042 blah, 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 and you times that by 60. If you do that, like this part times 60, you're going to get the second equivalent. So therefore, we say our total time is going to be 173 minutes and 3 seconds. I just want to thank you guys for coming to this end of my channel, and if you've enjoyed the content so far, just go into my channel page, hit the subscribe button and hit the bell for more notifications, and if you want, you can do personalized or all, and that way you won't miss any future maths or educational videos. Anyway guys, thank you for watching and see you next time. Ciao.